The next part of this module, we are going to be exploring various periodic trends in the periodic table. So let's just take a look at this simulation. And what it's going to show us is the relative size of an atom with respect to some other items in our everyday life. So what we're going to do is we're going to sort of zoom in, and we're going to start off with the coffee bean. And if we keep zooming in, we see some single-celled organisms and their relative size in micrometers. So we're getting smaller and smaller and smaller. There's chromosomes, lysosomes, mitochondria, which are organelles, part of the cell. There's viruses. Now we're getting into nanometers, and there are 1 billion nanometers in a meter. So we're getting quite small. You can keep going and going until we get into picometers now, where there are 1 trillion picometers in a meter. There's the size of the water molecule, and there's the size of the atom at 340 picometers. So when we are measuring size of atoms, we are obviously on a scale that is super small. So it wouldn't make sense to measure sizes of atoms in millimeters or centimeters. We need to get as small as a unit called a picometer. And when we are measuring the size of the atom, we are going to be measuring the atomic radius. Now, the radius is half of a diameter. When we are measuring radius, we are looking at the distance from the nucleus to the outermost boundary of the atom. Now, how do we go about doing that? We must take 2 atoms side by side of the same atom, and we must measure the distance from the nucleus of one atom to the adjacent nucleus of the next similar atom, and then we cut that in half, because you need something that is massive enough to measure from one point to another. So that's how we go about figuring out radius. Here are just some relative sizes of the hydrogen, which is 30 picometers, and fluorine. Again, 2 similar atoms side by side, distance from one nucleus to the other, and then we cut that in half to figure out our radius. We're also going to be looking at ionization energy as another trend. What is ionization energy? It's the amount of energy needed to remove a valence electron from an atom, usually in its gaseous state, so in gas form. The units for energy in this case are something known as a kilojoule per mole or an electron volt. We'll talk a little bit more about that as we get into chemistry calculations, but what you need to know is how much energy it takes to rip off an electron from the valence shell is what we refer to as ionization energy. And again, when we remove electrons, we form cations. We can remove more than one electron from any given atom, and we would refer to that as first ionization energy, second ionization energy, or third ionization energy. And you can see here, when we remove one electron from a sodium atom, it requires this much energy, 495.8 kilojoules per mole. And if I go to remove a second electron, we notice that we are having to take that second electron from a full octet, a full valence shell. So you can see the great increase in energy required. We go from 400, 500 kilojoules to now close to 4,000. So it takes much more energy to remove an electron from a full shell. And that's also due to the fact that we have increase in positive nuclear charge because it's holding on to fewer electrons now, holding those electrons more tightly. So it requires more energy. The last trend that we're just going to define, we're not going to necessarily graph this trend, is something called electron affinity. So this is how much energy is given off when an electron is added to an atom to make an anion. So when atoms gain electrons, okay, what happens is that incoming electron gets added and there is a release of energy. That is called electron affinity. And again, when we are measuring electron affinity, it is measured in kilojoules per mole or electron volts. Remember that nonmetals tend to want to gain electrons, so they have high electron affinities compared to metals, which tend to want to lose. So they would have lower electron affinity.